shows that equation like in a graph form?
Yeah, there's actually several places. Let me find one that's more specifically what we want it to be. Probably in 2.6. Here we go. No, 2.6, 2.7. Page 143 and 144 shows this one visually and that one visually.
143, 144?
Yeah. And again, the whole idea is I have, if I want into the slope there, at some A, I have to have 2 points to find slope. We've known that since algebra. But I want into the slope right at that point. That's why we did the whole limit discussion, so we see how they work, so then I can use them. And our goal was to use them to find the slope there, the instantaneous rate of change at that point. So that's why I let h go to 0, so that this thing eventually, in the limit as h goes to 0, that's sitting right on top of the other point. That never happens, so we always have 2 points. But to get as close as possible. You with me? So I do find that instantaneous rate of change right at that point. Maybe. So the secant line is a good, it's not the best point in the world to use, but secant line is a good approximation, but I want to let them get really close so I get exactly what the slope is right there. Right? How do we feel so far about that? Okay, one person says yes, that's good. That's all I need, just one person. Okay. All right, so we have all these things that basically mean the same. These two are specific points. This is the most interesting one because it itself is a function. So we understand that functions assign values to inputs. They have at x positions, the y position is understood by the function. You guys with me? That's a really strange way to say it. F prime says, okay, at that point you know what the value is, but F prime tells me what the slope is. What direction is it going? That's really good to know. The plane is right there. Okay, I know where it is. Where the hell is it going? That's what there's a meteorite. Is it coming at me? That's what F prime. F says, there it is. F prime says, it's going that way. Oh, thank God. Okay, they're in trouble. We're fine. You guys see the difference? And I told you before that knowing whether to use F prime or F becomes huge later. If you plug it in the wrong one, you're getting wrong information. If you plug it into F, you're getting where the function is. If you plug it into F prime, you're getting what the function is doing. What direction is it going at that point?
Velocity and stuff?
You can think of it as velocity, but it didn't have to be velocity because the function could be anything. If the function represents position, then F prime would be a velocity. Is that cool? But velocity is a little too specific of a way to look at it.
It's kind of cool.
I can take that. That's more than I normally get for math. Okay. Blah, blah, blah. Does that help out a little bit? I mean, I can't remember the specific question that was going on. Does that help out?
Yep.
A few of you guys looked excited. The rest of you are all like, please let this stop. Okay, I'm going to steal this. So. You're okay? All right.
Designated cameraman.
All right. Stay.
You gonna plug it in now or wait?
Huh? Oh, yeah, thank you. Actually, it should be good. I actually had time to... But I know better than to assume anything. If you make an assumption, you make an ass out of you and us. All right. So let me just go through this little worksheet real quick, and then we'll jump into review. We'll do whatever the hell you want to look at. All right, little dude, you should be good. Okay. Let's point you there. All right. I didn't want anything that was going to be too much, and this borders on not enough, but this should be enough to get us going with this. So we'll start off nice. This should be nice because it's basically algebra with a kink in it, right? I mean, algebra deals with straight lines. What is the slope of this line here?
-1.
All right, so here's the whole idea. When I want to graph, so this right here is f. I want to graph f prime. So you can be very specific. I'm going to try to be a little bit specific, but not crazy specific. Here, I'm just going to want a shape, a rough sketch of a shape. I'm not curious if you get exactly the right slope and all that kind of stuff. But here I can get exactly the right slope because it's just a straight line. So back here, the slope is -1. So at that point, the slope is -1. At that point, it's -1 all the way back here. That's what's going on. What about from up here? Yeah, +1. So it's +1 up here. Now, what's interesting is what the hell happens right at the kink. And this is a very, I think I told you guys, at the cusps, at these sharp corners, it's not differentiable. And you can see why. It's almost like a continuity thing. The derivative from below is not the same as the derivative from above. Right? And this is why physically we can't do this. If we do this, we are dead. This is a little bit too much acceleration to handle. Right? So that's why actually at 0, it just doesn't exist. So open circles both places. You guys with me so far? And I don't know if you remember, we discussed this a little bit, but it's getting your mind to click in correctly as far as how to look at this. Let's look at this. This is a little more interesting. Just a tiny bit. A really good place to start for drawing f prime is where the slope is 0, because that's the most obvious places. Where is this thing 0?
On the peaks.
On the peaks and the troughs. I love it. So the slope is 0, like right here. The slope has a value of 0. So everything in purple is the value of the slope at that position.
Is there a reason why you're drawing it down?
There's an exact reason why I'm drawing it exactly where I did. What is the value of the slope here?
0.
0. So I put at 0. If the slope was 1 there, I would have put it at 1.
Trying to correspond graph.
Exactly. So in purple, I'm putting the slope of the function. So f tells me the value, the output. This would be where the plane is, or whatever it is. In purple, I'm drawing what its velocity is at every point. So if this is something on a roller coaster or something down here, in terms of up and down, it's not going up and down, it's flat. So it's not changing at all. And then suddenly I'm climbing, and then again, it's flat here. Right? So when I throw a pin up in the air, at what point is its velocity 0? If I threw it straight up and down? At the peak. Right? Yeah. Or if I had a yo-yo, same thing, where is it 0? When at the trough, when it's down. Yeah, we know so far. So it's not bad. It's easier sometimes to talk about in terms of velocity, especially when you can bring roller coasters into it. Where else is it 0?
At 0.
Yeah, this is just a coincidence, right? The function value doesn't have to have a damn thing to do with its slope there. And here's the key thing. Look back here. This might be easier to see with this. If I picked that absolute value up and just moved it up 100 places, so now this is at position 100. How does this change? Doesn't change a damn bit. So the function output, the slope doesn't care what the hell the function output is. That's where it is. Slope doesn't care about that. Slope just talks about where is it going. Right? No matter where this thing is, it's always going down at a rate of 1 y per x. And then here it's freaking out, and then here it's going up 1 y per x. Okay, maybe. So again, it's just coincidental on this one that it matches. If I pick this thing up a little bit, I'd still have a purple dot right there. How we doing so far? Alright, so here's where I'm going to be a little less specific. Those are my anchor points. I like to call those my anchor points. What kind of slope is it back here? Negative. And it's very negative here, and then it's gently kind of sloping off to 0. Right? So basically here, it's really freaking negative. I mean, this tangent line is like crazy. So I'm going to have pretty big negative here, and negative 1. It's going to be pretty big negative, and then it's going to eventually slope down to 0 there. Now what's going on here? Whatever this number is, it's going to be a big negative number. That's why I put it down there. And what's happening is slopes are going to go around the corner here. They're still negative, they're still down, but they're not as down. That's why it's less and less and less negative. I'll let you soak that in. It's one of the freakiest things to get used to. That's coming up. Yeah, it's hard to see it on this one because it's such a steep slope. And if actually the point of inflection would probably be back here. We can see it here. And what happens after this point? What happens to the slope now? It's positive, and then it goes to 0 again. So somewhere in here, it's the biggest positive in this whole region, right? So right now it's small positive, and then it's bigger, so it almost kind of follows this. This is where you have to be careful. And it's going to go to 0 here, right? So somewhere in here, I really hope you guys are with me, because it has to go back to 0, so it's got to slope off again. So somewhere in here, it's got to be the biggest possible slope.
So it's going to go like this?
So it's going to go, yeah, it's going to have a peak in here, and then it's going to go back to 0. So right here, it's going to look almost parabolic in here. Do you see that? Because it's 0 slope, then it increases to the maximum, and then it has to decrease back to 0. But what's really easy is when you're doing this, you kind of start to follow this, and everybody gives me, it's the same thing. All my functions are the same, Jeff. No, it's because you got trapped. You got to really pay attention to this. This is why I call them my anchor points. I know I've got to get back. If I'm doing this, I'm like, oh shit, I'm supposed to be there. It's because it reaches maximum here. So if I go up, this slope isn't bigger than that slope. It's sloping down to 0 again. You guys kind of with me? Mm-hmm. This is very strange. So basically in here, it's got to go. Let's see if I can go through here gently. Oh, it's great.
So the velocity is still increasing, just not as fast.
Exactly. So whenever you hear people talking about the economy, this happens all the time, especially with the economy. You're like, the rate of loss of jobs has slowed, or something like that. And you're like, we're still losing jobs. Right. It's just not. What people are hoping is we're doing this. That's what they're looking for. They're looking, when are we going to turn that corner? Right. So if you really, on first blush, people are like, oh, cool, yay! Wait. Then you really think about it, wait, no. But then the economists are like, yay, maybe we're making that turn, and we're not going to do this thing. Okay, sure. Like a cube, right? We're hoping it's going to be more like a square. We come back up. Cool. You guys semi with me? But you hear that kind of term all the time, especially when you're talking about the economy. The rate of growth has slowed, or the rate of inflation has slowed. You're like, well, it's still going up, but not as bad, not as much. Okay, maybe. So you hear derivatives all the damn time in the news. In fact, you hear second derivatives and third derivatives all the damn time in the news. Because right now, we're just talking about the rate of growth. Isn't growth itself a rate of change? So the rate of growth is a rate of change. Right. It's how quickly how quickly my slopes themselves are changing. So let's leave that for later. Just a little future thing to look for. What happens after this point? And it goes negative.
Super negative.
Yeah, it goes stupid negative. I like it. Right? In fact, this is going to approach infinitely negative. It's in the limit. It's getting more and more negative all the way down. So really focus on what. This is a crappy ass job on my part, but this picture here looks pretty much like what? Yeah, gravel. And this original thing could have been something like a negative x cubed, because it's, you guys with me? Yeah. And remember the shortcut we talked about a little bit that we're not really using yet, but I'm just going to talk about it again? When you do derivative of x cubed, you should end up with 3x squared. There's a negative out there, so you end up with this downward parabola, exactly like it should. And in the homework, you should be doing these with that limit definition. Limit is h goes to 0. There's one with x cubes and x squares in it, and that's a lot of fun. Then we have this function. Looks like Grossman from above. It's the Grossman function. You guys try that one. I, of course, leave the hardest one for you to try on your own. Maybe do it in pencil, just in case you need to erase. Or even do it on the other side, if you can see through.
Don't make a mistake, don't use it correct.
Where do you always start? Anchors. Where's the slope 0?
There's 3 of them.
All right, cool. So plot those first.
This is where it's biggest numbers.
I like it.
Find the biggest numbers, you do a bunch of
It's like barely.
Makes you think of it like here slash slope.
Yeah, that's.
And then like there was where I thought I could do this thing where if it was negative here, then it would be positive here. But that only happens in the beginning. I don't know why.
Well, right now, it's
Like,
really
make
just
a
that. Make sure that no it's past here. More negative. Somewhere in here, it seems to be starting to get more positive. So I'd actually move people over just a little bit. This is what you put on the test. Right?
negative here, and like our original functional stop being. So that's another point.
Well, I think it's like, even if it's like this, we would be here. If it was like this, yes, it's still really good.
Zero.
Really good. Zero. You got zero here,
The maximum. That should be another 0 back.
Well, back, right?
Okay. Looks like it's a little bit off. It's 0 right there. So everything you're doing is getting more positive. The slope, you know, slope is 0. Slope back here is negative. That's why you're down. Then it's 0. Then it's back. So right from here. Slopes up. And then it's getting that's the function of the slope is getting shit of yeah. Alright guys,
Yeah, I missed it. I was like.
give me some approximations for putting zeros. Well, one of them is -1. Not 1.
1, 2.
Yeah, like right here somewhere, maybe right there. Right, is where it slopes off to nothing. Before that. About 3 it's also. Roughly 3. Those are my anchors. Those are what's going to always make sure I'm going back towards them at the right time. Slope starts off really big, negative. And then it goes gently into that good night. Okay. And then right in here, it goes from 0 to a little bit positive and back to 0. So somewhere in here is going to be the peak. So it's going to peak about right there and then come back down to 0 slope right there. How are we doing so far? So again, when we're drawing on top of this, we're drawing what the slope is doing. And that is such a weird thing to keep in your head as you're doing this. That's why it's really easy to just kind of start following the picture. Now, where in here, so it seems like anchor points are good. And the second thing that's good is about where should my peak or trough be. And it looks like it's going down, down, and it looks like it's starting to pick back up around here. So I'd say the trough should be in there somewhere. So my next little parabolic thing, it would have the trough here, and then back up there. You guys with me? Because it's definitely getting more and more and more negative until it reaches the maximum negative, and then it's getting less and less and less negative to 0.
That's like the pen going up in the air and then coming back down. It's losing its slope in a way.
Sure. And then after that,
About the pen? I don't know.
the pen was mostly just to talk about the where is it 0 slope. Yeah. And then after that, of course, it just gets big, more and more and more positive. Now, the original function, what was that look like? It's about like this was about an x cubed up here. This would be what? Look at the end behavior. How many turning points are there? 1, 2, 3 turning points with up. It could be 6, but I'd say 4. It might be 6. Who knows? But I'd say 4.
How did you get 4 out of this?
Because there's 3 turning points.
3 turning points has got to be at least a 4th degree thing, right? This is one little thing you should remember, or at least have heard back in pre-calc, and now it's coming back to you. Cool. And because like a parabola has x squared, it has 1 turning point. Cubic could have at most 2 turning points, and so forth. Look at our derivative. The derivative of this should be 4x cubed. So it should be cubish. Sure enough, that's cubish. Right, that purple that I've drawn, that is cubish. Yeah.
So you said that has 4 turning points?
3.
So, it has 3, okay.
Yeah, yeah. 4th degree because it has 3, so it's at least 4th degree, if not more. Even, of course, so it has this end behavior here. Now, real quick, everything I just discussed, if you didn't go through graphing hell, that would have been a much longer discussion. You understand what I'm saying? So pre-calculus gets you to a point where I can talk about calculus without having to explain end behavior and all that kind of crap. You should know it, and if you don't, you should quickly remember it.
Well, the test is going to ask us what degree do you think this would have been to?
Too bad, I don't know. Maybe. So you might
Yeah,
be-
don't like that idea.
Alright. Alright. Everything's cool. Any questions on that idea? It's not the easiest thing, especially if you still haven't quite had it click in your head yet exactly what's going on. But you just have to continue to remind yourself. Do those anchor points. Then look for your little, where's the most negative slope? Where's the most positive slope? That should be the peak of what you're drawing. You shouldn't go past that. Those kind of things keep you on track. Okay. Are there any specific questions from homework? Yeah.
Oh, yeah. Oh, never mind. I had my question on the homework, but then it's somewhere else. Page 140, number 24.
Okay, so number 24 says the limit as x goes to negative infinity. got square root of 9 x cubed plus 1. Okay. So here's the funny thing to me. If I put up here what would this be? 3. Right? You guys with me? Now, that is essentially what this is. Because what's the square root of x to the 6th? X cubed. And the whole, now if you want to do it technically and by the book, that's cool. And I have colleagues that are so anal about this, and you have to be anal at some point, but this is not really the place yet. But if you want to do it by the book, you have to, and this is actually a good thing to show you guys, because I know a few people had trouble with this. I have to divide by the largest power. And this should sound a little familiar, at least for some of you guys, from what you did in pre-calc, before you talked about the shortcuts, the 3 things. I don't think we didn't look at radicals in pre-calc, though. So you would divide by what? X cubed. I like it. So up here, can you divide by x cubed?
No.
So on the bottom, I'm going to divide by x cubed. On the top, what exactly am I going to do? 1 over x cubed is also known as square root of x6, right?
Since we're getting so big, so we're going to negative infinity or positive infinity, could we technically just think about the x and the 1?
Yes, good.
And do the,
I love it. So right now I'm going to do it by the book.
oh, okay.
And then there's a few other ways you can do it, considering that we're letting x go to infinity, so who cares about x compared to x to the 6th?
Yeah.
This eventually, is nothing. But you guys get this point at least, because you do have to use this idea at a few places in the homework, where you can divide by a radical of 6 just to get it in there. So now this becomes what now? Radical 9 minus, I like it, over 1 plus 1 over x cubed. So when x goes to negative infinity, these things go to 0, right? And I really don't have to worry about the negative infinity part, because these effectively have the same, well, this is where you have to be careful about it. The output to this will always be what? Positive. So this upper is always positive. The output to the bottom one, as I go to negative infinity, is negative. So when I go, x goes to negative infinity, these two go to 0. And then what do I get here? Square root of 9?
3.
It's 3. Do you have to worry about this?
No, because it's going to negative. Because they're equal coefficients, or they're both x cubed.
Because root 9 is something.
Because we didn't have to worry about that before when we didn't have radicals involved here, did we? We didn't have to worry about that. But remember, when you're putting larger and larger values of x in here, the top is positive. It's got to be. It's a radical, so the outputs has got to be positive. And you're cool putting negatives in there, aren't you? Because your 6 power and then minus a negative is positive, so it can handle that all day long. The bottom is negative, 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 all the way. So that's the one place you have to be careful about this, is the radical. That's the one thing the radical does. Effectively, it's the same thing we did in pre-calc. Especially if you, whoever suggested this, say that actually doesn't really matter compared to x to the 6. Screw him. So square root of 9x6 is 3x cubed. But where's that kind of break down? What is the square root of x squared? Absolute value of x. Right? So really, really what's going on here is you're getting, let's see, where can I throw this in? Screw it. I just always thought about it that way. So at the end I know this has got to be negative 3. So if you graph this thing, you should see that behavior. I don't know if anybody tried to graph this. Yeah.
I got a little confused where you got the 1 over x to, or square root of x to 6, and like how you got to the next step. I missed that.
Oh, so now since they both have square roots, you can just pull that x6 inside. So it cancels here. X over x6 is 1 over x fifth.
You cross cancel and then.
Yeah, just brought that inside. And then it can cancel
And
down.
the answer's -3 because it's going to the negative.
Because you're getting positive values over negative values,
Which will always be a negative.
which would be negative answer. Yeah.
That's not because they're negative infinity. Negative infinity is separate from what he's talking about.
Well, no, it is because of this. When I'm going to negative infinity, I'm getting positive results
You're
here,
going to the left side.
and I'm getting negative results here.
Okay, yeah.
Cool.
I just wanted to say it didn't automatically be.
Yeah,
negative.
exactly.
It's
The negative there doesn't mean that it's definitely negative at the end. You're right. Because if that would have been to a 4th power, that's to an 8th power, then they would have
They're both positive.
both been positive, would have been fine at the end. Yeah.
So how come you got 1 over x to the 5th and 1 over x to the 3rd? Is that just from that last number?
So here, x over x6 is x5 on the bottom. Here, 1 over x cubed is just 1 over x cubed.
Oh, yeah.
Just looking at power of x, that's why the powers end up kind of off. Because there's an x inside there, it's going to take 1 x
So you
away.
take each number, it's like you distribute it.
Exactly.
Okay.
How do you want this answer?
What's that?
How do you want this answer written on the test?
Like that?
Circle the -3.
Yeah, that's it. I want a little bit of a symbol somewhere as to how you're considering the sign.
But I mean, you didn't want it to be limit x approaches negative infinity of f of x equals -3. You don't want to like longer.
No, you've already done that. Just say equals -3, you're fine. Yeah.
So 1 over x to the 5th over 1 over x to the 4th, we cancel each other?
No, definitely not.
Or they.
What is happening here exactly?
Yeah.
What's the whole reason we do this? Is because we know 1 over x to a power higher than 1 goes to 0. Right? I mean, 1 over x to the 2nd, 1 over x to the 1st, all those are going to go to 0 when x gets really, really big. Right? So if I introduce those, then I have these finite numbers left, and I have these pieces that are going to go to 0. And hopefully, like I said, some of you guys, this should look familiar from pre-calc. Normally, right before you talk about the 3 things, the 3 possibilities, they're the same powers, they're higher at the bottom, they're higher on the top. Normally, you've done a couple that look like this, where you divide by the highest power, just to see why things work the way they do. Yeah, and you're all like, that's a long time ago, John.
So for the denominator, it's 1 over x cubed. I thought you couldn't have that at 0. You can't. You're dividing by 1 by 0. Right?
Nope, nowhere. Letting x go to infinity, so I'm dividing 1 by big, which is fine. It's just it goes to nothing, right? 1 divided by small goes to infinity. That would be the problem. Yeah.
Can we do the next one? I mean, not the next, but number 30.
Number 30? Oh yeah, good. Alright, one of the weirdest things with infinite limits is what happens with sine and cosine. Sine and cosine, the whole idea of limit is what? Do you guys want the answer?
Oh, yeah.
I thought you might.
Appreciate it.
What's it mean for there to be a limit as x goes to infinity? What does that mean has to happen with the function if the limit exists at infinity? There's really only one side to consider here. If I'm going to infinity,
Let's end up somewhere.
there's no other side. That would be weird.
So say that, ask the question.
You can't just.
So as
It has to get to
for this to exist, what's that really have to mean has to happen? As I go to infinity, if f approaches L, it's sideways.
Means the domains are infinite.
The most easy way for that to happen is this, right? That's the most common way. That's the way we're used to, right? With the functions we do. But it could be anything as long as, what does this really embody? What idea does that embody that limits are all about? As I get closer to this, which in this case means as x gets big, my function's values have to get Close to L, arbitrarily close to L. I'm not going to bring epsilon delta in. I'm just going to, the language itself is fine. Epsilon delta is a little technical. But I've got to get close to this eventually. Arbitrarily close, if this limit exists. What does cosine do forever? Forever. Is it getting closer to something?
No, stop.
No, in fact, this is exactly what it looks like at 18 billion. Right? 18 billion to the billionth power. This is what it looks like at infinity. Shit, it looks like this. It's not going anywhere. It's not getting close to something. So then what is the limit as x goes to infinity of some cosine function?
1.
It's not 1. Is it getting really close to 1? Does not exist. And we call the reason for that is because it oscillates. It doesn't get closer to something. You can find infinitely many places at any position close to infinity where it's 2 away from 1, right? Here, not there, but here it's 2 away from 1. Here it's 2 away from 1. That's not getting arbitrarily close forever to something. So it never gets close to something, ever. So the ideal limit is it's got to get close to something and never get further away again, ever. That's the idea of limit. At some point, it's got to do that. If it suddenly goes, nope, and you're like, shit, maybe now further. Nope. No, screw it. It doesn't. That's exactly how it sounds to it. Yes.
Can't sine or cosine wave get closer or closer?
Only if they're damped. So that's when you have something like, and that's not what this problem is, by the way. What's the big difference between this and the actual problem that you're asking me about? In between here and the problem you're asking me about is plus sign. Here, these are multiplied. What is this doing as x gets really big? It's getting really small. It's going to 0. Right? So this is what you call, this is kind of cool. If you graph this in your calculator, it looks basically like this. That's damped oscillation. That's what physically happens. You pluck a guitar string, it doesn't keep going at the same thing forever. I feel like the world would be just, pluck, going, no, not another one, it's never going to stop.
Inertia, right?
Yeah, the string is eventually going to be brought back by frictional forces, and that's embodied in this term. So you get the physics far enough, you start thinking, well, what coefficient goes here, depending on what the string's made out of, what the density of the air is, what the temperature is. That affects what's going to go in there to tell me how quickly it's going to dampen down to nothing. You guys semi with me? A little bit? Semi? Okay. That's what's going to happen here. Ain't going to happen here. Oscillation. So if I have the limit, what's that actually say? After all that talk, it says e to the negative x. That's cool. As x gets really big, this gets really small. That's part's awesome. Plus, shit, cosine of 2 cosine 3x. So that's fine. That part does not exist. So the whole thing does not exist, right? Weakest link. If that was multiplied, it would be fine. That would kill this eventually, right?
So the limit for e to negative x is 0.
Beautiful.
And then the other one does not exist.
Does not exist because it's oscillatory.
It's on its own.
I like it.
So cosine and tangent will always have it does not exist. I mean, cosine and sine will have that.
And in fact, tangent too. I mean, tangent is a little bit stranger, but as you go to infinity, it's actually weird. It's always, draw it correctly. It's always going from negative infinity to infinity. Negative infinity to, it's even worse.
So that doesn't have a limit either.
That doesn't have a limit either.
So
For the same kind of reason. But
anytime you get a trig function, it's just going to be does not exist.
Well, you got to be careful if there's any modifiers or anything. Yeah. And I mean, secant and cosecant, they have the same problem, right? But what about inverse trig functions?
No.
Inverse tangent. What's the limit as inverse tangent? What's the limit as x goes to infinity of inverse tangent? No, Jeff, got it. What's inverse tangent look like? Looks like tangent, just
Flip.
and what's this? It's an asymptote. What's the value? Yeah, pi over 2. So the limit is x goes to infinity, tangent inverse is pi over 2. Pi over 2. So that's why I want to be careful. Don't just say that to yourself, because then you'll the minute you see any trig, you'll go, oh, that's fine, it's fine.
So you just want to memorize that stuff though,
This is stuff you should know.
Yeah.
But now you're just applying it in a different way. You know what inverse tangent does. You're supposed to know what it does. Now you're looking at it in a little bit different way. Being a little more specific about things. Yeah?
What modifiers cause it to exist?
Well, you know, like that. Where the amplitude is a continuously decreasing function. You guys with me? I mean, what's this amplitude here? 2. All right, 2, negative 2, 2, negative 2. That's not... Here, this is the amplitude is always getting smaller. Therefore, the whole thing is going to go to 0. I said damped oscillation. And E is one of the most easiest ones, but it could be anything. Cosine... Good Lord, Jeff. Get a little organization here. This is bad even for you. You know, if I had limit as x goes to infinity of cosine 2x over 2x. What do you think? 1. This one is too easy. I think you're trying to think about 0. Be careful. It's as x goes to infinity. The top is effectively a constant. Let me let you absorb that. A constant means it doesn't go to infinity or negative infinity. It's effectively a constant, somewhere in between -1 and 1. Right? But the bottom is going to infinity. So what's constant over infinity goes to 0. Cool. That again is acting like a dampener. Because what does this do as x goes to infinity? This is 0, so it's just dampener, just like e to the negative was. And again, e to the negative is just 1 over e to the whatever the hell I had up there. Can't even read. It only goes to 3. You with me? That's 1 over something. 1 over some x kind of thing. So it's the same idea, exactly the same idea here.
So that's just an example of when there's a trig function that actually does have a...
Because it's been modified somehow. The amplitude is some decreasing, or it has a limit. So that's the 0 actually. It's got to be a 0 limit, because if it's not 0 limit, then the oscillation here kills it too. It's got to be 0, so it's got to kill it. Yeah.
So a constant over something that goes to infinity is always 0?
Definitely. Right? Yeah. That's why we divide by the highest power of x. That's why. Because we're trying to create all these little 1 over x5, 1 over x4, 1 over x squared. Those are all going to go to 0 when x goes to infinity. Does that make sense? That's why we do that. And we did that, and then we developed those 3 rules. But then some teachers only teach 3 rules, and that sucks. Okay. Anything else from?
27.
Oh yeah, this is gross. Yeah. This is one of those I definitely expect a question on. And they don't say this anywhere, but you have to assume A and B are not 0. It can be anything. So you're going to get possibly get some expression dependent on A and B. So I can't remember now. I was going to look earlier if they have an example. I don't know how. Here we go. Yeah, they do. They have an example that shows exactly what to do. It's just, the example, of course, is a lot easier than this problem. It's the exact same process. Does somebody know what to do with this on the first step? Good, multiply by the conjugate. It seems really weird because we're going to introduce a fraction where there is no fraction, but basically, why can't I not handle this? This turns out to be infinity minus infinity, which sounds like it should be 0, but it's not necessarily. It depends on if one of them is going to infinity faster than the other one. Let me let that sink in. Does that kind of make sense? If he's going to infinity faster than this guy, then this difference is not going to go to 0. It's going to either be some constant or it's going to go to infinity itself. You guys semi with me?
Would it be bad to break like into 2 problems with fractions at all?
Yes. It would be.
has a lot more work, or it can't be done?
I'd have to think about if you. No, you want this. You want to investigate this difference.
No.
That's what's making this thing hard to do. You can't investigate each of these by themselves, because by themselves they go to infinity. End of story. There's not really too much to do with them. I don't know if that makes sense right now, but yeah. So I really want to investigate this difference because I know it's all about which one's going faster. And much later in this course, we're going to learn something about limits and the rates of how quickly something's going somewhere. It's called L'Hôpital, some French stuff. That's in our future. Right now, we got to suffer with this. So what is the conjugate?
Plus, same thing.
Same thing with a. There you go. That's the way I would say it. Same crap you got up there, Jeff, except the plus in the middle. All right. That's exactly right. So I'll do the bottom. Isn't that nice? I'll do half of it. Oh, come on, it's not that hard, right? Conjugate's all about difference of squares, so it's easy. So what do you got on the top? X squared plus AX. Yeah, don't forget that minus has to go through the whole thing. It's got to affect both of those. That's key. So that's nice, because what happens? X squared goes away. So then I get, and here's another reason why we do this. Can't I attack it like we just attacked the last problem now? What do I mean by that? I mean dividing by the largest power of x. And what's the largest power of x, effectively, for everything? X. Right down here, I'm just going to do 1 over root x and all, or root x squared. So here I'm going to do 1 over x. Here I'm going to do 1 over root x squared. You guys with me? So now multiplying the conjugate sort of makes sense. It made this ratio that I can then attack with that normal procedure we have. That's kind of making it fall into something that looks more familiar. So on top I get A minus B. On the bottom, what do you get? Is that cool for the first piece? X squared over x squared is 1. AX over x squared is A over x. We'll let that sink in. Because all I'm doing, if you want to do this for yourself, this is all I'm doing. Right? Because all I'm doing is dividing everything by radical x squared, which is the same thing as x. That's why it's legal. I'm not doing something different to both top and bottom. They're the same thing. So, of course, what do you get over there? Incredibly enough, it's the same damn thing except with a b in it. This kind of kicks ass. What happens? What do I definitely know what happens here?
The a over x and the b over x go to 0.
Kick ass. Square root of 1 plus square root of 1 is 2. So this limit is a minus b over 2. That's some freaky ass shit. It's really technical way to put it, but if you make a 4 and b 2, the limit of this is 4 minus 2 is 2 over 2 is 1. The limit of this is 1.
Why did the a over x and b over x?
Oh, because I'm letting x go to infinity. And again, this is a constant divided by something getting really, really big.
Okay.
So it's going to go to 0.
Okay.
And again, that's the whole reason why this process exists. It only works really for limits at infinity. Yes?
One thing that my buddy showed me was when you first look at that problem, draw a line under it, put a 1 underneath it, maybe that inherently makes you think of that a lot quicker.
Could be.
I don't know if that helps anybody else in there, but
Maybe.
it just automatically makes you think of that as an equation, not an equation, rational with square roots in the top that you have to attack like that.
Yep. Could be. So that works for you. We'll put this all over 1.
I must miss something. How come the top is being divided by x and the bottom is x squared?
Who wants to help me out on that?
It's just square root of x.
Alright, cool. Like, So it's when those radicals are involved that lets us, I mean, it doesn't let us, it's just we have to convert it. Like the earlier one we did, x cubed was the same thing as radical x6.
Right, you can't divide in there until...
Exactly. I like it. Okay, cool. Very cool problem. I mean, I don't know if you guys even are thinking about what this means. Only if what is true that this limit is 0. Only if A equals B. Only if they're the same. That's the only way to make this limit 0. If A is bigger than B, then this limit is positive. That means that this is going to infinity a little faster than that. But it's at like it comes out to a finite number. It's really neat. I don't know if you guys believe me or not, but I'm not going to waste time right now doing this, but you could put a value in for A, put a value in for B, and y1 equals that, y2 equals that. Just look at the functions, see what they do over time, if you want. It's the difference in those functions that somehow comes out to be this value, because that's really what this is getting at. At infinity, what's the difference in these? It's that. It's really kind of neat. Okay. Or not. Anything else from...
Speaking of homework, or
we can do a practice test. Let me go ahead and give you the answer key here before I lose anybody else. And the thing with this is, if you haven't tried the practice test out, and maybe you don't have time to do it, maybe don't even look at this. If you do the practice, don't just look at this and agree with me, right? Oh yeah. Yeah, that's what I would have done. Right? I mean, that's not going to do a damn thing for you to agree with me.
You're going to have calculators on stuff?
Oh yeah. Oh yeah. You always have to show me work. Definitely no phones, no laptops, no anything like that. Make sure you got a front and back on this here.
Can we get one more? I think you can do the rest.
Yeah.
Can you do number 5?
I think, who was asking me, were you asking me something before I started handing these out?
Yeah, I had a question on,
And then I'll do 5.
I had a question on 10, C, and D. Both of those give me a hard time.
So that's sort of like that one we just did
They shouldn't.
a minute ago.
No.
And that's not an easy one until you see how it really works. And the whole idea of a limit not existing because of oscillation. Because it doesn't really narrow in on something. It can't make up its mind. Right? So that limit can't exist.
I would say you didn't do 5 now.
But real quick, if I saw something like this, something to a negative power, I would immediately rewrite it like that. And that's just my brain kind of latches onto that a little better. But it's very obvious that the bottom's getting really, really big, so the whole thing goes to 0. Right, so just rewrite these negative powers on the bottom. It's a little easier to kind of look at. And then part D is exactly like the one we did. The amplitude is always decreasing, so the whole thing's going to 0. It's going towards 0. Even though the sign doesn't make up its mind, we force it. There, you made up your mind. Right? You know I'm going to have a problem like number 11 on there. It's probably going to have a couple more requirements than that. I like that kind of problem because you get a lot of problems in the book about, here's a graph already, tell me some stuff about it. I like to give you, and you've seen problems like this in your homework. Create a graph that has this happening, this happening, this happening. Yeah.
You changed my mind on what problem.
You did what?
I changed my mind on what problem I need help on. Can I have help on number 2?
Alright, and let me do, was it you that wanted 5?
Yeah.
Okay.
This is the f of x I've never really seen that. It's like cube to the 6 or whatever.
Well, that's just the 3 in front of a 6th root.
What does
So it's
that
a 3 coefficient in front of a 6th root.
I know what like a cube root means.
Do you mean the 6th root by itself?
Yeah. Does that just mean like what 6 times to equal that?
Oh, yeah. I mean, once you understand what a cube root is, you know what all roots are.
Okay.
Right? So the 4th root of something is what does it take 4 of to multiply to be that thing?
Right.
Period.
Okay.
Yeah. But the important thing here is, like when I ask about domain, why would this thing have a restricted domain? Or does it?
Square root has to be
It's an even root, therefore the inside has to be bigger than or equal to 0. Right? And the way I argued this, and this is the perfect way to argue this, we say the inside, so if we're talking about domain, the inside has to be greater than or equal to 0. You cannot solve this directly. You can't get x squared by itself, take the square root of both sides, because that's a non-order preserving thing you've just done, which is this weird sounding word. But really, what you want to consider then is think about this graphically. Greater than or equal to 0 is easy. What's above the x-axis for this graph? So what are the x-intercepts? -2 and 2. This is a, what kind of parabola?
Yeah.
Down. So where is it greater than or equal to 0? From -2 to 2. So that's the domain of f. Not a damn thing wrong with that.
What would the range be actually?
Now remember, we saw one like this in the, I think it was in the first bit of homework, that we had to consider the extremes. Right? What's the absolute smallest this thing can be? 0. You put anything else in there, it's going to be bigger than 0, right? And since I'm subtracting it from this, what's the biggest that this thing could be? What's the range go up to? It's going to be when this is 0. So it'll be 3, 6, 3 to 4. That's the biggest it can be.
Is that how you want it written?
Yeah, yeah.
So not what that comes out to on your calculator?
Oh, no. I don't want to see a decimal crap. No.
Oh.
Yeah. I mean, the idea leads you to what this answer is. I really would rather, if I see decimals in too many places, it makes me start to wonder how much was done strictly on the calculator instead of by hand, right? So I'd much rather see this more often, because this tells me, okay, you understand the idea, you got the exact value.
Can you repeat how you got the range again? Just one more like the.
Well, I haven't finished it, right?
Oh, well, no,
So-
the first value, the y.
Oh.
Yeah, that.
I'm looking at this function, and the biggest this function can be, the biggest output, would be if this input, this result was the smallest it could be. Does that make sense? And this is exact reasoning we used on that problem from the homework when we did that one in class together. You're all like, okay, sure. We'll look that up on the video. Now, what's the other extreme? Obviously, the other extreme is if the inside is 0, that would be the whole thing is 0, so that's the smallest it could be. We already knew that. It's a 6th root. The smallest it could be is 0. It can't go negative. And that's in the domain is x equal to 2 or -2 does make that happen, right? Okay, so there's one little thing I just jumped at. Anything else from the? Yeah.
Okay, so number 2D, is it about even odd functions?
So what is the test you do to check even and odd? Even. That's good, John. Even, odd, symmetry. Test. What's the one thing you look at to see what kind of symmetry between these two it would have?
X equals f negative x.
F of negative x. You look at f of negative x. If this equals f of x, the same thing, that's even. When I square -2, I get the same thing as if I square 2. Even. If it equals the opposite of what it would have been, that's odd. When I cube -2, I get the opposite of what I would have gotten if I cubed 2. Let that sink in. It's exactly what we call them, even and odd. X squared even, x cubed odd. Right? Okay, cool. So if you look at, f of x, equals that. So what's f of negative x? Just plug a negative x in, right? And of course, what's negative x squared? X squared. Yeah, x squared, which is the same thing as that used to be. So that's even. Just somehow people do this kind of thing and they think those negatives cancel and then you get all screwed up. You just have to understand the basic idea of algebra about substitution. When you substitute something in, you better make sure you apply this to the whole thing. That negative can't escape being squared. That's what makes this even. The only place your input is here. And it's to an even power. It makes sense this is going to be even. That's the only thing that has an x in it, is that one piece. Okay. So what about G? G is easy, right, hopefully? If you put a negative x in for G, careful. Maybe not easy. Shoot. So I get negative x minus 5 over 7 plus 3x. Now what's negative g of x? That's negative 1 times, what was she again? X minus 5 over 7 minus 3x. Are these equal to each other? Hell no. So g of negative x is definitely not equal to what g was, right? This is different from g. And it's also not equal to what negative g of x would be. So is it even or odd? It's neither one. So don't get stuck in the trap that it has to be one or the other one. It definitely doesn't have to be. I can draw a parabola very easily, make it not, oh crap, it's not even anymore because I pulled it over a little bit. Right? Now it does have symmetry around its own axis, but to be officially even or odd, to be even, it's got to be around the y-axis, period. Very stringent definitions, or around the origin. If I move something a little bit, it's screwed. Right? That's why more often than not, if I just pick a random function out of the air, it's going to be no symmetry at all. Then H. H hopefully would... What's the only powers you see in there? What kind of powers are they? So it's going to be odd function. You plug a negative x in. H of negative x. You get negative 5x cubed plus 6x, which is the negative of 5x cubed minus 6x. So it's the negative of what h used to be. That's exactly odd. Cool. Yeah?
No, it's going back elementary, but 1D, why does the inverse exist?
1D?
Yeah. Like I said, we're going back elementary.
Let me see, what was the... page 70... Oh yeah, okay. What test tells you that something is a function? Vertical line test. And then what test tells you that that thing is one-to-one? Because the vertical is saying every x can have only one y. That's why every vertical line I draw is for a specific x. So if it goes through more than one place, it has more than one y. One-to-one says, okay, correct. Every x has to have one y, but every y also has to have only one x. That's a horizontal freaking line test. Exactly the same way we get a vertical line test. I don't know. I'm hoping a few of you guys were with me through everything I just said. Right? It's almost silly how much sense it makes. Where did the vertical line test come from? Why does it exist? It's the same damn reason the horizontal line test works for one-to-one. Because every x goes to one y, every y goes to one x. That's why it's called one-to-one. I can always find where it came from. That's why it would have an inverse. That's why inverse means be able to go backwards. Right? So if I have a thing like this and I say, what gets me 4? What gets me an output of 4? Well, shit, it's 2 I don't know what it was. I don't know what it was. Shit, I don't know. It's too bad. So this definitely does not pass the horizontal line test. There is an output that has more than one input. I can't find out where I came from. That's at the center. That's the heart of what an inverse function means. I should be able to undo what's done to get back to where I started at. Cool. Okay. Floor is open, yeah.
Okay, number 12, do we need to put the values, we actually need to calculate?
Yeah, I did very few values, didn't I?
No, do we need to calculate values, like do we actually need to divide pi over 2? Or we just put like pi over 3, pi over
Oh, I see. This is you're right. Good point. This is a little weird because I'm going to pi over 2. So to be completely honest, I just set up a table on my graphic calculator table, and I made an input pi over 2 minus 0.1. Pi over 2 minus 0.01. You see what I'm saying? So I'm getting closer and closer to pi over 2 from below. Pi over 2 minus plus 0.1. Pi over 2 plus 0.01. So if you look at the numbers on my answer key, and on the test, I'll be a little more specific in my table. I'll ask you to do so many entries, whatever. Here I just did it very quickly, but see the 1.4708? I'm pretty sure that's what you get when you do pi over 2 minus 0.1. Try it out. Pi over 2 minus 0.1, you get 1.47, blah, blah, blah. Is that all right? Because that's what you're asking, right? Is how do I figure out...
Like, do we put actually like pi over 2 minus 1, or do we have to calculate for this pi over 2 minus 1?
You can just put that, that's fine. I mean, but once you do it, it's there. You might as well put that too, it doesn't matter. You know, as long as I see your inputs and then your outputs, and then I can see the progression, right? And I like to do this kind of thing where I see where they're going in the middle. Right? Oh yeah, squeeze theorem. And the squeeze theorem,
I thought you'd have like 3 functions and prove that the middle one is...
yeah, you create your 3. You have one that you're working with, and then you create 2 that bound it. Right? So there must be something inherently bounded inside your problem. Of course, what in here is inherently bounded? Sine. Now look at that. There's all kinds of weird shit going on inside the sine function, but the outputs are going to be from negative 1 to 1. Yeah, I don't care what's happening on the inside. It's not going to affect the outputs of this thing. Okay. So therefore, this piece is always, like you just said. Now watch how I can build this. Maybe this will be cool for some of you guys. It's always in between negative 1 and 1. So what if I multiply all sides by this? Right? Then I'm going to get negative x minus pi cubed is less than or equal to x minus pi cubed sine stuff less than or equal to x minus pi cubed. And then I apply the limit to each piece, and that's the squeeze factor. Right? You focus on what part of your function has bounds to it. You explicitly write those bounds, and then you put in the rest of your function. And then you can focus on what's happening to this guy as x goes to pi, and what's happening to that guy as x goes to pi.
And that you're just plugging in pi, because that's what the limit's going, right? You're plugging pi in for
Yeah, these two have no problem at pi. They are continuous through pi. They are just polynomials. So I can just plug pi in. So you've effectively taken your problem from, I can't just plug pi in, because this has a problem of pi. I don't even want to try to take care of that problem. I've now made it 2 easy problems. They're polynomials. I can just plug a pi in now. You guys see that? So here's the thing I want to know something about, and I actually don't touch him. I do this and this. But because these both go to... That's not the best notation in the world, but just to get there quicker. That goes to 0. That goes to 0. Therefore, this has to go to 0. And this looks really weird. But this is not illegal. 0 less than or equal to something less than or equal to 0 means this has to be 0. That's the only way that makes any sense. Yeah.
So would it be the same steps if it was like radical or something like that?
Yeah, your steps will be exactly the same. You can't use squeeze theorem unless there's something bounded in your function that you can then use to set up this inequality.
So what would your answer be?
0.
You would be doing all that work or showing that it's you're improving.
Exactly.
What other things in there could be bounded other than design?
And trim, yeah, and then trim functions.
Well, you could have, let me see.
Are we getting too deep into this? We are, we stop. I don't want to derail.
I mean, you can have, e to the x squared. That's not good. E to the negative x squared, that's what looks like that. Right, so it technically is bounded, but I mean, that's not a very good example. No, I don't know. Off the top of my head, I can't think of it. Trig functions are what you see normally in there, because they've got the natural oscillation.
U7.
Oh yeah, okay, that's the one I was expecting. So, I mean, 7, I tried to show everything. There's my little side work there. And then here's the proof. So this says prove that the limit as x goes to 2. Where'd it go? 8 minus 3x. Negative 2, right? Negative. Equals 14. So then, given epsilon greater than 0, we need delta greater than 0, such that if x minus, x minus negative 2x plus 2 is less than delta, then
8 minus 3x.
yeah, let me just write f of x minus 14 is less than epsilon. All right, plug in your f. Yes, ma'am.
Do we need to write given epsilon
Yes.
greater than
Yes. Now I'm just writing this right now, just so everybody can see how the things need to look.
So that's the way it's supposed to be.
Yeah. Yeah. What you can do now, this is before I've done my side work, but you can say, given epsilon greater than 0, we let delta equal blah, blah, blah. Then if this less than delta, so x plus 2 less than blah, 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 and then you work out this. This is the idea behind any epsilon delta limit proof. Is that's what you want to show. And very often we would say, WWTS, we want to show. Right, that would be kind of like setting things up for us, ourselves, yeah.
The absolute value of x plus 2, we got it from, like, simplified.
Yeah, x minus negative 2.
Oh.
The whole idea is as the distance between x and negative 2 gets smaller, then the distance between the outputs and 14 also have to get arbitrarily small in order for that to be actually the limit. Right, that's the whole idea.
So you take a third of epsilon?
Yeah, where did I get that from?
Because you...
So here's the side work.
Agree between the...
Alright, so side work. Put in there what it is. 8 minus 3x minus 14. That's an epsilon. What am I trying to get from here?
X plus 2.
X plus 2, because then I can explicitly see what delta has to be to make it true. So I'm constructing from where I know I want to end up, I'm constructing where I have to start. I'm creating the thing I need to make this work. And that's where the cheating, it feels like we're cheating a little bit. Well, what the hell, man? You want me to do something? However I can figure out how to do it, that should satisfy you. So leave me alone. So if you do this...
8 minus 3x plus 14.
Negative 3x.
No, whatever.
Negative 3x minus 6.
Yeah, negative 3x minus 6. Does everybody understand what happened here on the next step?
Now.
Yeah, what's the absolute value of negative 3? 3. All right, let me let you guys soak that in. This is exactly what we were talking about earlier when I said you can only do this if when you rewrite it, it's now a 2. Right? Because the square root of 4 is 2, so I got to write it as a 2 outside. Absolute value of negative 3 is 3, so I took a negative 3 out, didn't I? That's the one step I thought might confuse people. But if I ever needed to, absolute values are kind of neat. If I've got that and it's supposed to be x minus 1, that equals freaking absolute value of x minus 1. Of course it does, right? Absolute value of 2 minus 7 equals absolute value of 7 minus 2. They're both freaking 5. You with me? So absolute values give us a little flexibility. You have to know what that flexibility is. But we do have it. This is more just exactly this idea. If I want to take a negative 3 out, absolute value of negative 3 is 3. And that doubly helps me out because that's exactly what I wanted to have happen. So now when I divide by 3, I know what I want to let delta equal, and I think you can see how I wrote it out from there on the answer key. Stay with me. Yeah.
So are these all the concepts that are going to be covered on the test? There's not going to be anything, no surprises?
I don't like surprises on my tests. If I'm taking them or giving them. So, no, I don't. I'm not planning on any surprises.
Okay.
I'll tell you, this is going to be a very teacher thing to say. Students will tell me it's a surprise or it's a trick question or something when it's not. It's just applying a concept that we know. So when you say all the concepts that are on here will be on the test, yes.
Okay.
Consider what that means. It's not going to necessarily... Somebody wrote to me and said, I'm not going to be able to be there tonight, but I wanted to ask, is the test the same as the practice test but different numbers? I said, you are a very optimistic person. No, of course not. And it actually goes further. It's the concepts that are on here. I might give you a different kind of problem that deals with the same concept. Okay. If you understand the concept, you should be able to do that. But I very rarely venture too far from homework problems. Right? I'm not going to give you something that's too far away from what you've seen in homework. Yeah.
10B. Okay, I got one quick question for you. Walk away from that one.
Yeah.
So when you pull the 3 out, and you write it as a positive 3 because it came out absolute value, then when you're doing the real work, you just have
you
to
can say,
remember that it's negative.
You know that this is the same thing as this.
Okay.
That's really what I meant. This is the same thing as this. Because the absolute value would kill that negative or leave it alone. You know, that's, you see that? That's effectively, so on the work here,
Yeah.
you just make it back into a negative 3 when you put it in, because that's what an absolute value allows you to do.
Just remember that.
Yeah. What's that? Oh, okay. So here's what I would like. Here's what I really would like to see: the proof. Given epsilon greater than 0, let delta equal to epsilon over 3. When x minus, I forgot what it was, plus 2, less than delta equal to epsilon over 3, then now you start doing all that stuff backwards, right? X plus 2 less than epsilon over 3, multiply the 3 up. I mean, this is where you basically just copy everything you did there in reverse. Less than epsilon. When you bring it back in, make it negative, because I'm allowed to and I want to. So then, some of you guys might realize I could have actually written this as 14 minus f of x, which would have taken care of all this problem. You guys see that? I could have written this as 14 minus f of x, less than epsilon. Same damn thing. And then I wouldn't have had any problem here with negative numbers. But if you don't, it's fine if you don't see that. Just want to point it out to you. So I have one more thing to worry about. Should I have done that? Shit, no. You're fine. And then I bring back in the 8 minus 3. So I think somebody was trying to ask me, and there is no, the epsilon delta proof is a very specific format. I think when you see this, you're like, how in the hell would I know to go from here to here? Well, you don't have to just know it. it's there. You know where you want to go. It's not like you're supposed to just suddenly magically know to break negative 6 up into 8 minus 14. You do it because you know you need 8 minus 14 in there, right? That's the process. Is always going to have where I start, where I want to end up as a part of it. So it's not, I don't have to somehow magically know that. You guys, I think somebody was asking me that, and that's what they meant. Was, how the hell would they ever know to do that? Because that's what you want. I mean, right? There. That's going to be arithmetic. And this is it. F of x minus L less than epsilon. So when this, then this is arbitrarily close to 14, so that means that is the limit. Yes?
Are you just want the proofs on the test, or are you going to put like problems where we actually have to find epsilon or delta?
No, yeah, I might have a problem like what you've seen in the homework,
Okay.
where it's like a concrete.
So it's not just proofs,
problem.
because there's been a lot of proofs.
Yeah. So the first few in that section were concrete stuff, and then there was a few like this.
Yeah.
So I can definitely, I'm not going to give you more than one of these because it's not that crucial of an idea, but I want to make sure you can at least try to set it up and get somewhere. And I very honestly could possibly give you a concrete one where I say, just like in the homework, if I want to be this close here, what would that have to be? Or the other way around, right? Okay. Just like in the homework. And that's when we have to know how to use that graphing calculator to set up your
The second
boundaries.
Intersection.
Yes. You want to find the intersection of those boundaries so you can work back to see what that x has to be, and then pick the smallest one for your delta, right? Just like we did in class. Cool. Anything else you guys want to look at? Yeah.
Someone asked for something.
Yeah, 10B.
10B? Oh yeah, so that one's a lot like the one we did earlier, right? Okay. And very quickly. And you're probably right. But how do I know I have to do anything? How do I know I can't just plug infinity in? I mean, this is where you got to be careful. I mean, an obvious one would be if I had this function. Don't start factoring it and doing all this weird shit. That's easy. Huh? But which one's going to infinity faster? Bottom one, so the whole thing goes to 0. Good. Right. So this is not really indeterminate, truly. This one is infinity over infinity, and they are the same, so it needs a little bit of work. There's not one overpowering the other one. They're lockstep, so I need to do a little bit of work to kind of get there. Some of you guys have probably already figured out the shortcut. Square root of 9 is 3. That's the corresponding highest power. Negative, it'll be, yes. Did I put that? It should be negative 1/2. What did I put? Oh, I put negative 3. Yeah, just to be different. Just to be, yeah. I divided one side by 3, but not the other side.
I get it now.
That's my fault. So 10b, the shortcut is highest power over highest power. So it should be negative 9, 6. Oh, negative 3, 6. That's what I did. Take a square root, negative 1/2. Cool. So I got a negative 3 halves down there. I always have to get at least one thing wrong on my answer key, just to show you I'm human.
I thought it was a test to see if you came back and said, this one's wrong. You have to cut it off.
But does anybody want to see the steps? I mean, we did one just like this earlier. So you divide by x squared on the bottom, by square root of x4 on the top. Same
So
kind of thing
we
happens.
showed our work as like we just crossed off 2 plus x and crossed off the 2x. Just like forgot about them and just made it 9x to the 4th over negative 6x with the square root on top. We wouldn't get it wrong if we just did it that way.
No, and in fact, I mean, that to me is better. But be ready if I say, show all of your steps or something like that, you know. Use the highest power idea to do your limit. I mean, if I say something like that, you better know how to do it.
So
Can you show it again?
yeah, so if you said that, how would you do it? Yeah.
See, I have no problem with, there's a ton of stuff that you desperately want to simplify and shortcut. But if you do a shortcut but you don't understand how it works and why this shortcut, where it came from, then that is not a good idea. Because then you get to the next class and the teacher's building on the stuff that you're missing. That connection between the concept and the shortcut. You're missing it. So how can you build on top of it? Right? I don't know if you guys understand what I'm saying. There's a lot of stuff in here that I'm going over that my students had to suffer before, and some of them are like, why do we got to do all this shit? It's because of this. You got to understand where things are coming from. Shortcuts are good, but not by themselves. All right, so on the bottom, I'm going to multiply by 1 over x squared. On the top, I'm going to do the same thing. 1 over x squared. So here I get square root of 9 plus
2 over x squared. Square x.
cube,
Oh, 3.
and over 2 over x squared plus 1 over x plus, minus 6. Okay, cool. So then that goes to 0, that goes to 0, that goes to 0. That effectively is exactly what you're telling me on that step. You see what I'm saying? But it's just knowing this and not forgetting that, because that happened to me so often in my career. I'd go further into the next math class, into the next math class, and I knew a shortcut, but I forgot why it worked. And then we'd be doing something that built on that idea, and I have to go back and say, why did that work, and then make the connection. The more you understand the underpinnings of things, the more connections you can make. And that's what's really important in getting far in mathematics, is making all these little connections.
Is that 2 over x squared? I can't really see.
Here?
No.
There.
Yeah.
Yeah, 2 over x squared.
Okay,